Institute of Inorganic Chemistry, the Czech Academy of Sciences, Strategy AV 21. Michael's Lab presents Interactions of inorganic clusters, cages and containers with light. This is Michael's Lab, and you are watching a new source of blue laser light, the inorganic polyhedral cluster Anti-B18H22. Anti-B18H22 emits 407 nanometer blue light and offers a laser efficiency of 10% and a remarkable photostability that is superior to the majority of organic laser dyes. Its three-dimensional cluster structure provides molecular strength and rigidness with molecular orbitals delocalized across the entirety of its 18-vertex polyhedral boron framework. This results in the very efficient conversion of UV irradiation into blue light, with almost zero losses to intramolecular movement. To improve laser efficiency, we are looking deep into the photophysics and photochemistry of Anti-B18H22, exploring the system's excited states and revealing its secrets. Our lab is also making new derivatives of Anti-B18H22, investigating the effects that different chemical substituents have. For example, alkylation of the 18-vertex borane cluster leads to better solubility and superior absorption and emission characteristics. Iodination of the Anti-B18H22 leads to intersystem crossing from excited singlet to triplet states and a beautiful green phosphorescence. This light energy can energize oxygen to produce its highly reactive form, singlet oxygen. Instead of iodine, we can substitute with SH groups. This thiolation of our laser borane provides a luminescent species that can self-assemble on metal surfaces to produce fascinating mono-layer surface modifications. Introducing pyridine ligands to our laser borane gives our molecule wings. These pyridine rings can freely rotate and flap. These movements determine the molecule's luminescent properties. Rapid movement gives lower intensity red emission. Slower flapping produces very bright yellow emission. In polymer-thin films, mixtures of the laser borane and its pyridine derivative combine to absorb light across a wide band gap and concentrates that energy to a single wavelength emission. A solar concentrator is born. Integration of our photoactive molecules into polymer materials and clays is enabling the fabrication of useful devices, including scintillators and electroluminescent displays.
And now it's my great pleasure to welcome you to our last event of this year, our Christmas Unicorn Deep Mind Lecture. And though we announced it as a Christmas present from us for you, it's even more like an amazing present for us to host here our today's speaker, who's Michael Londesborough. And probably most of you know Michael as a popularizer of science who show impressive experiments that cover broad range of scientific topics. But today he's going to present and speak about his research in his laboratory that he runs at the Institute of Inorganic Chemistry, Czech Academy of Science. And it's going to be about boranes, it's going to be about their light, and definitely and almost literally it's going to be exciting. So, Michael, the floor is yours.
Thank you very much. Thank you very much for the invitation, both to Sizzy and also to your good self. And what a wonderful place to talk. It's kind of, I like it how it's sort of organically styled, with a purine molecule up there at the top, and of course this used to be the place where the coal was kept for the institute, and I want to move away from carbon hydrides and talk a bit about the boron hydrides today. And I'm going to talk about, what happens when the boron hydride molecules get excited. So my main focus in my research work is to understand what happens when these molecules become electronically excited. And I hope today I'm going to teach you all a bit about that and hopefully get you excited into the sort of chemistry that we're doing in my laboratory at the Institute of Inorganic Chemistry. I let play in the background there a video which sort of highlights some of our work over the last 10 years or so, which has been focused on these polyhedral cluster borane compounds and how we can use the chemistry to engender interesting photophysics to get all sorts of interesting light phenomena coming from their molecular excited electronic states. But let's begin maybe at the beginning. You might notice this ship. It's the Titanic, and if you look very closely here, you might recognise these two. Do you? It's Jack and Rose, and Jack and Rose, of course, are happy and excited, maybe, and they're happy. Why? Presumably you think they're happy because they're in love, but the real reason why they're happy is because it's 1912. And 1912 was a really important year for chemistry, because in 1912 this gentleman here, Alfred Stock, a German chemist, he synthesized the first hydrides of boron. Because unlike carbon, which has, of course, photosynthesis, which enables us to rip out the oxygen from oxides of carbon and implant hydrogen in its stead, then there's no other natural form of such a process on this planet. So all the other hydrides we have to make. And it was Alfred Stock who made the first boron hydrides in that infamous year when the Titanic sank in 1912. And Alfred Stock, he was the student of the Nobel Prize winning Emil Fischer, who actually got his Nobel Prize for working out the structures of the molecules, such as the one you've got above your head there. So he was the first person to actually assemble the atomic positions in molecules such as that above your head. And he was the first person to realize, as he says in his acceptance speech in 1902 for his Nobel Prize, where he remarks on that through the work of his and others, the veil behind which nature has so carefully concealed her secrets is being lifted where the carbohydrates are concerned. So it was through his work that chemists could understand molecular structure. And he realized that so much of nature, in fact all of nature, is based on these hydrides of carbon and carbohydrates. He did finish his acceptance speech with a really poignant comment. He finishes, however, it is increasingly obvious that the one-sided study of carbon compounds cannot suffice to elucidate the nature of chemical processes in all of its aspects. So he understood that our planet uses organic chemistry to create its diversity, but he was intelligent enough to suggest, well, why should it stop with carbon? Can other elements do some other interesting chemistry? And of course, it was his student Alfred Stock who took that to heart, and it was he who chose boron. He also played around with silicon, but he chose boron because, of course, it's next to carbon in the periodic table, and he found and discovered that, indeed, boron is capable of making a very rich and diverse family of hydrides, the boron hydrides. Now, this is where our Institute of Inorganic Chemistry begins to take its role in the history of this particular field of chemistry. So this is, you'll recognize here, this is the Vltava Valley, leaving Prague's just around the corner over here somewhere. We're probably just over the tops here at the moment. And here is Rzesz, Husinec Rzesz, and our institute is over here where I've got my lab. a beautiful place. And it was in this sort of what was then a top secret research facility, carefully hidden away from any potential harm of imperialist bombers during the Cold War, that a group that was largely set up and driven by this man here, Jaromír Plešek, and another Stanislav Hrmanek, who's standing here. And these two really drove boron hydride chemistry in what was then Czechoslovakia. And their main goal was to develop new rocket fuels based on the hydrides of boron. Because in the same way as we use the hydrides of carbon to drive our vehicles and provide us with warmth through the oxidation to form carbon dioxide and water, well, the boron hydrides also have an affinity for oxygen and readily oxidize. And when they do so, they form borate and water, and indeed release per volume a lot more energy than the carbon hydrides. And with it, a very beautiful green flame. And anyway, so that top secret research being undertaken here in Czechoslovakia at Rzesz led to the discovery of many new molecules and many very important syntheses. But this work was, of course, secret, but nevertheless, once it became declassified, it was Plešek and Hrmanek who were very skillful at, first of all, publishing a lot of work, a good number of seminal papers regarding the syntheses of these compounds. But perhaps even more importantly than that, they put together the first ever meeting of international boron hydride chemists. And indeed, the institute received this plaque from a number of these international chemists, three of whom are Nobel Prize winners, thanking the boron group at our institute for this initiative. And it's something which, of course, is maintained till today. And this was the first ever IMI boron. It was an international boron chemistry conference. You might recognize this as Liblice, which is, of course, a chateau which still belongs to the Academy of Sciences. Thoroughly recommend a romantic weekend there. If you're looking for a present to buy your loved one. But there they are. There's including, as I said, some rather famous chemists in this group. So after declassification, thankfully, the main goals of the chemistry were no longer their simple combustion as a rocket fuel, but it began to go into a lot more high-tech understanding of the chemistry. I think that there was a phase which roughly continued until about the time I came to Rzesz, where the main goal was to expand the number of exotic molecules of these boron hydrides and really expand the synthetic procedures that are available to produce these compounds. And I think now the focus is very much on a deeper understanding of the molecular behavior of these compounds, both in terms of their chemistry and their physics, and their potential utilization, their potential application in a number of fields. So let me perhaps begin with a little sort of simple, because I want you to leave today feeling that you've made your first step to become a boron hydride chemist. And so I'm going to introduce you. This is one of the most important compounds that we have. The green balls are atoms of boron, and the white are atoms of hydrogen. So if you're quick at counting, you'll see that this molecule is B10H14, or decaborane. And decaborane is a commercially available compound. It's a crystalline, stable white solid. So it's something which many chemists begin with. And just to give you a few simple starting concepts, the cluster, so you can see why it's called a cluster, because obviously, unlike the carbon hydrides, which form sheets, planar sheets or chains, the boron hydrides form these three-dimensional polyhedra, which we call clusters. And in this cluster here, this 10-vertex decaborane cluster, the electron density tends to sit towards the bottom of the cluster, in the same way as if we had a bucket of water or a bucket of electrons, then that's where the electrons density tends to collect. Therefore, then it's no surprise that if you do some electrophilic substitution chemistry, so a halogenation or an alkylation or something like that, it tends to happen on these basal boron atoms in the cluster. And conversely, if we're interested in doing a nucleophilic addition with, for example, 2 electron ligands and similar, then the attack is at the top of the cluster where there is less electron density. How many of you here are familiar with boron hydride chemistry? Okay, the two at the back, I know that because they've been in my lab for quite a while, but you'll see here something which is perhaps slightly unusual, certainly for an organic chemist, and that is hydrogen atoms which look at first appearance to be divalent. Of course, that would be impossible, considering that hydrogen only has 1 electron. What you're actually seeing here are 3-center, 2-electron bonds, where we have, this is what's called a bridging hydrogen between 2 boron atoms, and this triangle with the 3 centers shares 2 electrons which are delocalized between the 3 center. And that sort of general principle of bonding is repeated everywhere. You'll see these are all triangular faced polyhedra. And again, these 3 boron atoms will also have 2 electrons shared between the 3 of them, etc., etc. Right? This, of course, means that this hydrogen atom here, this proton, rather, is very acidic because it's sharing its little electron density that it has in this 3-center 2-electron bond. So the boranes, these bridging hydrogens, as opposed to these exohydrogens, which are classical 2-electron 2-center bonds, these bridging hydrogens will easily deprotonate. And when we take off the protons and the reactivity changes, after which we can begin to insert heteroatoms into the cluster. For example, carbon to make carboranes, or metals to make metalloboranes. We can insert sulfur, phosphorus, many other p-block elements. And indeed, a lot of the really important work on carbon insertion was done at our institute at Rzesz, at our Institute of Inorganic Chemistry. Right, but what I'm going to do today is talk a bit about what happens if we give this molecule, a bit of some alcohol and some pellets of potassium hydroxide, a bit of drugs and alcohol. Then if you do so, then it does become a bit of a rock star, especially after you oxidize it with some iodine. And what you do is you remove 1 vertex on that 10-vertex system to form a reactive nonoborane, a 9-vertex system, which will then clip together to form what's called a macropolyhedral. So there's 10 of those. It's 2 of those. There's 2 of those decaborane-like structures. Can you see, which are now linked by a boron-boron shared edge. Okay. So, and this compound has got 18 atoms of boron, 22 atoms of hydrogen. You get B18H22. Okay. Now, this molecule, in fact, the man who first was able to discern and elucidate its structure is this man here, Lipscomb, for which he won the Nobel Prize in understanding the molecular structure of the boranes. And this particular boron hydride happens to be by far my favorite. And I've spent many a year studying this, and I'd like to say that perhaps I might well be the authority on boron, on B18H22 chemistry as it stands now. Now, the compound exists as 2 isomers, okay? Syn and anti-B18. And they differ by which boron-boron edge they share, okay? So here you can see an anti-B18, it's sharing these two here, and in the syn, it's sharing these other two here. So it's just a slight difference, so they're isomers. Same number of atoms, but same empirical formula, but a different structure and how those two subclusters are conjoined. And I became interested in these compounds during my PhD. I was involved in doing all sorts of metallation reactions with these compounds, inserting different types of metal centers, platinum, palladium, nickel, etc. And after my PhD, I then I started to work on the use of these compounds is as a dopant of boron into silicon for the production, the fabrication of p-type semiconductors, which have what's called an ultra shallow implant. And the principle is that you, instead of firing single atom boron compounds in doping silicon with boron, you fire these big clusters, and the kinetic energy in which this ion beam of boron hits the silicon, the energy is spread not on one boron atom but on 18, and that leads to a shallower implant and therefore a smaller device and a faster device. So it was used for the fabrication for top-end semiconductors. And so I was working on this for a number of years, and one of the things I was interested in doing is the effective separation of these two isomers. These two isomers are produced in their synthesis, in equal proportion. And of course they are physically quite similar, and therefore one of the tasks I had was, could we separate the two isomers effectively? And one of the avenues I was pursuing in their effective separation was to use chromatography. So that's the idea of a solution of a mixture of these two isomers being passed down a column, and that column is essentially filled with high-grade sand, a silicate, and as it's passing through, as it's falling through to gravity, their slight differences in solubility will lead to a separation on that column. Both these compounds form colorless solutions. However, what I did notice was that if I was performing the separation on a sunny day, I noticed that the column began to glow. And it began to glow a really beautiful blue color. Now this surprised me simply because I've been working with this compound for a number of years, most of which of course were in Leeds in England, where there's not so much sunny days as there are here in Prague. It's often rainy and overcast there. So I'd never ever actually noticed this property. And so it really went completely past me. Plus as well, I wasn't really interested in any of the physics or the physical properties of the compound per se. I was more interested in its chemistry and how I could change that compound. But seeing this physical effect in front of my own eyes made me go back into the literature, and I started to look if this was actually being documented. And the only thing I found in the literature was in the initial publication, the preparation of a new boron hydride, B18, this is in the mid-60s, by this man, Frederick Hawthorne, who's working in California at UCLA at the time. And he's really, a great boron chemist who's done so much for the whole field. And in his initial publication in 1962, the only thing I found about this property is that he wrote solutions of the hydride in hydrocarbon solvents, referring to B18H22, exhibit a purple fluorescence. 3 ultraviolet absorptions are observed. So he just, at the time, of course, this is the 60s, and he probably thought nothing of it particularly. He just made the same observations as I made, perhaps seeing it in sunlight, and this purpley blue fluorescence. And he just measured and listed the absorptions. So that made me think, maybe I should follow this up. Maybe I should look a bit deeper into this. thus began the work. So here's a whiskey glass with a solution of anti-B18H22. And this is what happens if you shine a UV laser into it at about 335 nanometers. Okay? You get this wonderful, beautiful, bluey purple luminescence. And of course, the first thing I did was I went to our UV Vis lab and put it into the spectrometer, and I confirmed the published absorption spectrum. Okay, so here we can see this is at the bottom, this is wavelength of light. So for the young gentleman here, blue light, your eyes can see from blue to red light. That's from about 400 nanometers to about 800 nanometers. Okay, you see 400 as blue. Okay, 500 is green. 580 is yellow, 600 orange, 800 red. Okay, that's what we can see. This is the intensity of the absorptions. And you can see here's the absorption graph, okay? And this is the absorption peak, which is the important one, at about 355 nanometers, which is UVA light. Okay, well, we can't see UV light, but it's the same energy which burns your skin if you sunbathe too much in the warm Czech sunshine in the summer. And here is the emission peak. Okay, and you can see a beautiful emission centered at about 406 nanometers in wavelength. So this is great, I thought. Define the actual emission. What else can we do? What else can we use in our laboratories to explore this a bit deeper? And this is something I think we should all, this is the responsibility of all scientists, is when you see something which is interesting, you should try and go as deep as you can. So I started to look around what I could do myself, and then I began to speak to people who had some expertise as well in the field. And I got to know somebody who was good at doing computational science on looking at the photophysics of various molecules, which is an important aspect. And this was the first computations with the man here, Oliver, who was from Spain, from Madrid. So I asked him to calculate, what was going on. What's the HOMO and LUMOs of this compound? Okay. So the HOMO is the highest occupied molecular orbital. That's where the highest energy electron is. And the LUMO is the lowest unoccupied molecular orbital. So that's the orbital into which an electron that is excited, it's the molecule that it occupies. Okay? And you can see here, now, of course, I quickly realized that essentially zero work had been done on understanding molecular orbitals in the boron hydrides in the context of luminescence. The molecules like that above your head, the organic equivalents, a lot of work exists, and there are all sorts of conventions how to discuss these orbitals. You'll be familiar with sigma orbitals and pi orbitals and pi starred orbitals from your coursework. And so there is an established molecular description, which in the boron hydrides there wasn't. And if you look here, at first glance, it looks a bit confusing. But one thing I want you just to concentrate on, if you notice in the LUMO, there's a node. There's an area of the molecule where the orbitals are not connected. Do you see that? Whereas in the HOMO, here, you can actually see that it pervades the entire molecule. Now that means that during absorption, okay, the absorption occurs into a molecular orbital which goes over the entirety of the two subcluster molecule, the macropolyhedral molecule. When it's excited, then it seems as if the charge is sort of split. And what happens is that comes with a higher energy, and what it wants to do is to snap back. And when it snaps back, it fires out a photon of light. And we can we can describe this whole process in such a diagram here. This is called a potential energy hypersurface. Okay? So here we have the molecule's ground state. This is when the molecule's just relaxed, just like normal. And it will absorb a photon of UV light, and then it will become excited. Right? And this is the first excited state, S1. Right? It becomes excited here. This happens extremely quickly. Okay, so quickly that it's very difficult to, using any instrument on Earth, to actually observe. So it's almost instantaneous. And then at this point here, the molecule relaxes a little bit to a local minimum. Okay, so it just vibrates a little bit. The molecule just vibrates a little bit, and so it goes from the hot excited state to this excited state minimum here. Right? You with me? And we can measure how long it's in that excited state, how long it occupies this local minimum. And in the case of anti-B18H22, remember one of the isomers, anti-B18H22, well, in case of this isomer, it remains in this excited state for a long time. A long time for a molecule, that is. And we can measure that time, and the average is 11.2 nanoseconds. Okay. Compared to its isomer, syn B18H22, which has no solution phase luminescence. That's the black curve here. The syn isomer becomes excited and then immediately releases the energy. And it does that just by movement, by vibration. It just wobbles off. The loss of energy from an excited state without radiation, without emission of light, has to go past this point here. This is called the S0, S1 conical intersection point. Okay? So in the case of the syn B18H22 isomer, this point is low in energy, and it just slips down very quickly, and it returns to its ground state. In the case of anti-B18H22, we have a massive 0.65 electron volts in the energy difference between its excited state minimum and this conical intersection point. So once it's excited, it stays excited for a long time, and eventually it gives up trying to get there, and it returns to the ground state through the emission of light. Is that all clear? Yeah? You say yes, Michael, no, Michael. Yeah?
Yes, Michael.
Okay, now, another thing I want you to notice is that this process, it's not just 2 levels. It's actually called a 4-level system. You've got your cold ground state, that's your real ground state, excited to a hot excited state, that very quick relaxation into the ground state, the excited state minimum, that's the 3rd level. And then the 4th level is this hot ground state, which it achieves by the luminescence, the emission of light. And then again, it just wiggles and it gets back down to 0. Okay? So there's 4 states in total. That's important for later on. Another thing we can do is this. We can measure the efficiency of this process. And we call that efficiency its quantum yield of fluorescence. This is phi here, quantum yield of fluorescence. And the quantum yield of fluorescence for this compound is an amazing 97%. What does that mean? That means for every 100 photons of excitation light, to get it excited, 97 of those 100 photons end up in emission as blue light. Okay? 97% efficiency. So it's really remarkably efficient at doing this conversion of UV radiation into blue light. But as, of course, exciting, capable, and skillful chemists, I hope you're now thinking the question that I asked myself at this point. And that is, what about the 3%? What about the 3% of the time where it doesn't go to emission of light? What's happening there? So as you see, at this point, we've done enough now to really understand the photophysics of this molecule and publish that. But going deep enabled the discovery of some new questions. And I followed that. So my new question now is, what happens in the 3% of the time where we don't get luminescence? So let's discuss that. Well, one thing that can happen is that statistically it's possible that the excited molecule can overcome this large potential energy barrier, and it actually does reach the canonical intersection point, and it will relax non-radiatively. It will just vibrate the energy without any emission of light. Very similar, if you can imagine, a very difficult, arduous and dangerous climb to the top of the mountain. And that happens maybe 1.5% of the time. Another thing we discovered is that there exists what's called a triplet excited state, which is rather low in energy. The triplet, of course, this is just about how the electrons, so you've got a singlet state and a triplet state where the electrons are aligned parallel. And what can happen is what's called an interstate crossing, intersystem crossing, where the electron transfers from its singlet excited state to its triplet excited state. Now this is a quantum disallowed process, so it's very improbable, but it can happen. And it happens in the case of anti-B18, H22, about 0.0003% of the time. Roughly once in every 100,000 excitations, this can happen, right? And we can measure precisely how frequently that happens, really with a great deal of precision. So, but although this 1 in 100,000 chance, which is roughly the same statistic as one of us here would get Alzheimer's in later in age, is enough for it to be measurable. And indeed, when we looked into changing the chemistry and how chemistry can influence the photophysics of this B18 compound, we later found that by adding big atoms, such as large atoms of iodine or sulfur at these positions of the B18 cluster, we can push the probability of this intersystem crossing to actually from almost impossibility to highly probable. So for example, this molecule here, this diiodine derivative, has a probability of intersystem crossing into a triplet state and afterwards phosphorescence of 59%. So we were able to discover that if we do some chemical manipulations of the cluster, we can shift the photophysics. And I'm going to come back to that in some detail later on. But nevertheless, a small fraction of that 3% is the intersystem crossing to triplet states. The other thing that happens, that takes place, is that the molecule, when excited, can absorb another photon and shoot up to an even higher excited level. S2, S3, S4, S8, it can keep going up. Of course, ultimately, it will have to fall back down to the S1 and then do its fluorescence or whatever the destiny might be. But this process does happen, and we explain this in very great detail in this article here. Now, this process of what's called excited state absorption, at the time, we almost neglected it. As the lecture goes on, you'll see that this becomes extremely important in really using this molecule in applications. But at the time, we thought once every tens of thousands of excitations, you get an excited state absorption and you go to an excited state. What we did notice is that if we keep pumping this molecule, if we pump it with energy, we keep exciting it over long periods with a lot of energy, we see a change. So this is, and we were using NMR spectroscopy to follow this change. Here's the NMR spectrum, the boron NMR spectrum of anti-B18H22. 9 peaks, because it's a symmetric molecule. And you can see this is after 15 minutes of hitting it with a very, very powerful laser. No change. After half an hour, no change. After an hour, little bits of change appearing. 2 hours, definitely. After 210 minutes, with an accumulation of 1.51 megajoules of energy, that's a lot of energy, then you can see that the spectrum has changed considerably. So this means that even though it's highly improbable that you do get excited state absorption, if you keep going long enough, if you keep pumping it again and again and again, something is happening in those excited states which is changing the molecule. That's why we see a different spectrum. And you can see now with all these different peaks, it's not just, there's lots of little peaks. That suggests that it's now become asymmetric, that molecule. If we then take this sample here, which as a sort of like a fingerprint, we can see there's other things in there. We take that sample and run its mass spectrum. So we look at the masses of this mixture. We can see that it's still dominated by, of course, B18. However, we see mass peaks for a substitution of the cyclohexane molecule, because all this was done as a cyclohexane solution. So we see an interaction between the cluster molecule and the solvent molecule, such that you get a single substitution with one solvent molecule, a double substitution to a lesser extent, and even some other chemistries going on. So we did find out, we did know that if we have the molecule in an excited state long enough and we keep pumping it with more and more energy, in the upper excited states, it becomes chemically reactive. And that photochemistry is important. Nevertheless, at the time, I was thinking this is just a wonderful example of how we can go very deep in our chemistry and physics, and how we can explain this 3%. I was then invited to go to Madrid to present this paper on the bequest of the gentleman who did the HOMO-LUMO calculations for me. And whilst I was giving this talk, sitting in the audience was this young gentleman, Luis Cerdan. And Luis Cerdan was a laser specialist, a physicist. And he immediately said to me, Michael, when I finished the lecture, does this molecule work as a laser? Can it be a gain medium for laser emission? I said, Louise, I haven't tried. So I took the plane back to Prague, got some samples, and got the next plane back to Madrid. And about sort of 5 days later, we did the experiment. And we found that indeed, it did work as a laser, which of course made it the first borane laser. And indeed, not just the first example of a borane laser, but the first example of a molecular inorganic laser molecule. All the other inorganic laser materials tend to be, these macro materials, these perovskites and similar type materials. So it's something that could be compared to the very well-known and often used organic laser dyes. Now, let me explain to you a bit about the differences between fluorescence and laser emission. So far, I've been talking about the fluorescence is an emission of light. It's a spontaneous emission of light. And usually, don't forget, remember we're starting at the ground state, and we're exciting it with UV light, 335 nanometers. We call that pumping, okay? We're pumping it. So we're pumping the molecule, we're pumping our sample with UV, and some of the molecules absorb that energy and become excited. Do you remember? Okay. Now, usually under normal circumstances, the pump is not very powerful, And therefore, if you can imagine a sample have many, many, many trillions and trillions of molecules, you only have a few molecules at any one time in this excited state. There's far more molecules here in the ground state, and you have a spontaneous emission. However, what happens if you pump hard? What happens if you pump hard and fast? If you pump a lot of molecules very quickly into this excited state? Well, what happens as you pump more and more and more, and you get a greater and greater population of excited molecules here, you increase the probability that the excited molecules will stimulate their own emission. And when you get that stimulation of emission, at that particular point, for every pump photon going in, you're going to get 2 photons coming out of the emission process. Right? So this then leads to a gain. It's called a gain. We're getting a gain of the light coming through, and that's the actual laser emission. Now you can see this in using different techniques. So if you're looking at your UV vis spectrum, what you see, the difference is, as you're getting towards stimulated emission and laser emission, then this broad emission peak becomes very narrow. Okay? That's the evidence that the emission that's coming through is stimulated, because when the emission is stimulated from these excited molecules, the emission comes at one specific wavelength, in this case 406 nanometers. Okay? So the light becomes what we call coherent. Yeah? Here is an important graph. This shows the energy of the pump. Okay, the energy we're pumping in here at the ground state. You can see here we're pumping, 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 pumping. This is all spontaneous emission. You see blue light, but it's still just spontaneous emission. But eventually you get to this point here where all of a sudden you're getting a gain in the light coming out. That's the laser emission. And you get this, at this point here, this broad peak will collapse into this sharp laser peak. This point here is called the population inversion. It's at this point where all of a sudden, statistically, you've got more molecules in the excited state than here. More molecules here in this third step than in this fourth step. At that population inversion point, that's when you get the higher probability for the stimulated emission, and that's when you begin to get gain. And as you keep pumping more and more, you're getting the population here is becoming greater and greater and greater, and dwarfing the population down here, and the amount of light coming through is increasing there. Are you with me? What makes a good laser? I mean, for me, this is my favorite laser in the world, of course, because these are my babies. So this, for me, is the #1 laser. But a person who's making money from lasers doesn't care whether it's B18 or ketchup. So what makes a good laser? What's going to make the decision for somebody working in the company whether they're going to use my molecule or not? There's 2 main parameters. The first one is the laser efficiency. That's simply the ratio of the energy in that we have to pump and the energy coming out through the emission. Okay? And it turned out for us that laser efficiency was 10.5%. So that's the gain. Notice that's very different from the efficiency of the spontaneous emission of light, which was 97%. This is the laser efficiency. So this takes into account the amount of energy you need to pump before population inversion. Are you with me? And that's the fraction. That's the gain that we get, 10.5%. You might think that sounds a bit low. It's not actually. It's pretty good. But unfortunately, not quite good enough. For comparison, a typical on-the-market laser, blue light laser, is running at about 30% efficiency. So we're about a third, to get into that market space, we're about a third of the way. However, that's one parameter. The other parameter, which is really important as well, is how long will this gain medium work before the molecule just blows apart. Eventually, molecules are like us. They still are suffering under the second law of thermodynamics and entropy in the same way as we're doomed to grow old and pass away. Molecules are also doomed to eventually break up and oxidize or whatever. So a measure of how long a molecule will last until it falls apart, okay, is its photostability. And what we did was we compared, in this paper in Nature Communications, we compared our compound, our B18, this is the black trace here, with the best laser materials used on the market for blue light. And you can see that our molecule comes, really, it's really good, a very high performance. It's better than the majority. Okay, it's not quite as good as this baby here, but almost is. But our laser efficiency is better than this one. So it's very highly competitive for the second major deciding factor on whether somebody's going to buy your laser, and that's its withstanding of really intense pumping conditions. So that gave us good hope. We're thinking, really, we could start thinking about, could we get these things on the market if we boost our laser efficiency? So then began the next challenge. Now we've gone this deep, we're going to have to go deeper still. We have to understand how our molecule, why our molecule is losing efficiency, which is linked to why do we have to pump it so hard before we get population inversion? Why is it taking so much time to go from here to here? That led us to think, logically, that the Achilles heel of our otherwise fantastic molecule is its absorption coefficient. In other words, the efficiency at which it absorbs light, the pump. Okay. And we discovered this by comparing it simply to the best on the market in the same, this organic laser dye here, diphenyl stilbene, which has almost overlapping absorption frequency and almost overlapping emission frequency. Can you see it? But if we look at the extinction coefficient, in other words, how efficiently is it absorbing? Okay. So what you do is you pass the light through a sample and you see how far that light penetrates before it disappears, before it's fully absorbed. And if it's very high absorbing, you barely see it enter into the solution, whereas if it's poorly absorbing, it goes further and further and further before eventually it's all absorbed. And that, you can see here how much more superior the absorption for this compound is over this compound. Now this compound is 30% efficient. So it seemed clear to us at the time, we found the problem. The problem is our baby doesn't like to absorb so well. Once it's excited, it's good. Once it's excited, it's up there. But he's difficult to get excited. So we had to start thinking, how do we help him get more excited quicker, faster, more easily? This is a big problem because absorption is an inherent property of a molecule. There's no textbook chapter about how to increase absorption efficiencies. So it meant we had to do it the hard way. We had to do it the hard way in that we had to just keep making new molecules and new molecules and new molecules, new derivatives of this B18 compound, and hope that one of them would absorb better. At the same time, an added complication is that it's only a few people in the world who are doing B18 chemistry. So it's not like the luxury of organic chemistry, where there's literally thousands of chemists working on different synthetic procedures, and there's many, many, many people working at developing syntheses. So there was essentially nothing known about the substitution chemistry of this compound. So we had to start from scratch. Indeed, the two gentlemen sitting at the top there know the difficulties and the challenges in this particular endeavour, and they have contributed to the syntheses of some of these molecules. Anyway, this is a bit of an overview. It's not all of them, but it's how many I could fit on one PowerPoint slide. But you can see there we've done thiolation, chlorination, bromination, iodination, alkylation. To a large extent, we began by looking to borrow organic synthetic procedures, some of which worked, many of which didn't work at all. So let me concentrate. There's many different stories here, and I don't want to keep you here all the way till Christmas. So I'll just tell you a couple. Let's look at this alkylation. Oh, before I do that though, is that this is something I'm particularly proud about. This is for the labuzhniki of boron chemistry. We've got now a large enough number of molecules that we're beginning to understand where substitution occurs on this 18 vertex molecule and why. And so you can see here, these are essentially the positions at which substitution is most likely to occur. And if we do the reaction with neutral anti-B18H22, these are the blue bars, then it almost all occurs at these at the base, at these 4 vertices, 4, 4, 1, 1, 3, 3. However, if you remember, these borons are acidic. If you deprotonate the molecule, then that changes where you start getting the substitution. And all of a sudden, this 7 vertex becomes really important. And there's all sorts of things I could tell you about this, which are fascinating for it might be fascinating for the two at the back there who've spent quite a lot of time working on these compounds. But this is really important because it's actually beginning to establish some rules to how substitution occurs in this molecule. But that's for another day. Let's concentrate at some alkylation. A lot of the synthetic work was done by this gentleman here, his name is Jonathan Bold. He's quite a remarkable man who, at the age of 70, rides his bike. For example, we had a conference in Rennes in France, 1,700 kilometers away, and he rode his bike there and back. So he's quite a magnificent chap, and he did a lot of work on these alkylations. And I just want to show you some of the statistics. From these alkylation reactions, we've got lots of different molecules. The main products are, in terms of methylation, is this one. So you've got methylation at the 4 and 3 positions on both subclusters. Okay, so 4, 4 dash, 3, 3 dash. And in ethylation, you get the same molecule essentially, but with ethyl groups instead of methyl groups. Yeah, same positions. Now, these two molecules, here's the important statistics of the photophysics. Look at the quantum yield now. So this is for anti-B18, remember 97% efficient. These molecules now are 100% efficient. So that means that remember the conical intersection point? That's gone bang up in energy, even higher in energy, and the molecule can't get there at all. It's stuck in an excited state, and when in this excited state, the only way to release that tension is to emit light. So you've got even better emission, although, of course, 97 to 100%. You've got, this is important, it'll be more important in time. This is just, remember, I just want to remind you about the lifetime of the excited states. Do you remember for our B18 H22 molecule, it was 11.2 nanoseconds. For the main products here, it's slightly shorter, comparable. This is an important graph though. Do you remember how we identified that the Achilles heel is the absorption coefficient, the absorption efficiency? So here in these groups, this black one here, this is anti-B18. And our two main compounds had a better absorption. Not much, but a better one. About between 8 and 12% superior absorption coefficient. So we thought, great. It's got slightly better, it's got better emission properties and better absorption properties. It must have a better laser efficiency. So with a great deal of excitement, we get our samples and we fly to Madrid, meet Louise, and we're straight into the lab. And the guy hates me because we're working all through the night and everything, and we're really excited, and what happens? Not only was it not a better laser, it didn't laze at all. And we were thinking, oh my God, what is happening here? I mean, this was a seriously depressing moment at this point, because all of a sudden I'm thinking all of our assumptions must be wrong. Certainly this concept that it's the Achilles heel is the absorption coefficient. So it was quite worrying. At the same time, especially after a glass or two of wine, is you're thinking, maybe this is not worrying, maybe this is even more exciting because we're wrong. And if we're wrong, it means that we've got a lot of work to do now to find out why we're wrong. To find a solution, we get back into the plane, return to the Czech Republic, and we go here. Does anybody recognize where this is?
České Budějovice.
Yeah, well done. It's České Budějovice. So we go to České Budějovice to try and find out what's going on. Why do we go to České Budějovice? Well, the reason is because they've got really good, fast laser facilities there. Okay? So we can, at our institute, we can do lots of good measurements with the UV-vis spectroscopy, but here they've got an extremely fast pump laser, okay, that can send out pulses, picosecond pulses of light. Okay, so this is really quick. Why is this important? It's important because in a picosecond, not even light can travel too far. Okay. Light can only travel, I don't know, a centimeter or two in such a small interval of time. This means that if we split a beam of light, the same beam of light on two paths, and we use mirrors just to prolong one of those two pathways by a few centimeters, the light then arrives at the same place with a picosecond or two delay. This means, if you remember the times we were talking about, remember the lifetime in the excited state for B18H22 was? Anybody remember for bonus marks? In nanoseconds, 11.2 nanoseconds. That's long compared to a picosecond. This means we can split the light with this laser system. We can use one of the photons to excite the molecule into the excited state, and then we can use the other to probe the excited state. Are you with me? So we pump and then probe. We pump it up, and then we've got another source to immediately have a look. Okay? This means we can explore what's happening in this excited state. In particular, is the molecule absorbing more energy in the excited state? You remember when we're looking at the 3% at the beginning, do you remember that there was that tiny probability that you'll get excitation into higher excited states. So this is what's important now, if you remember that. And this is the output, okay? So this is absorption, right? Positive absorption means it's absorbing. Negative absorption, of course, is emission, okay? The black curve here is anti-B18. So you can see in this area here, this is when you're getting net emission, right? This is the absorption, this is all the absorption that's going on in the excited state. So you can see here for all these, so this is the black is the B18H22, and the red and the blue are our tetramethyl and tetraethyl B18 substitutes. Yeah, remember the molecules we took to expecting to see lasering. And you can see here that in the case of our methyl and ethyl derivatives, you never ever, only fractionally here maybe for the methyl, you almost never get any real emission coming, negative absorption. This means that in the excited state, it's absorbing all the light, even the frequencies of its own fluorescence. Remember the fluorescence for these species is about, for the methyl and ethyl, about 420 nanometers. So it's absorbing in its own excited state, its own emission. Are you with me? B18 does that a bit, but not a lot compared to these two. So this region here you've got a lot of absorption, but this is in green, yellow, orange light. It doesn't affect us. Because what's important is the pump frequency, that's 355 nanometers UV light, and then the emission frequency. In the case of B18, 406. In the case of methyl and ethyl B18, it's 420. This is an important point. I want you all to, do you understand what I'm saying? So these molecules are absorbing their own emission in the excited state. I want you to really understand, because it's key, so I'm going to use this graph to help. Remember the 4 levels. Ground state, this is the pump level, it evolves to a metastable excited state minimum, and then if it emits, you go to the hot ground state, and for laser emission to happen, you need the population of excited molecules here to be greater than the population of excited molecules here. Yeah? What's happening in the case of this tetramethyl, tetraethyl derivatives is that here, when they are here, they're absorbing both the emission and also they're absorbing the pump frequency. So they're taking energy away from here, and they're taking the energy from here and they're going up and then coming down, going up and coming down. It's almost as if they've got like a hamster sort of cycle here. So they become excited, then they absorb that emission, they go to even promote to an even higher excited level, then they fall back down. They can then emit as emission of blue light, or they can once again excite them, absorb that energy. Then it's all about the quantum probabilities, and you can measure those. And what we measure is that it's more probable to absorb that photon of light here than to emit it. And it's also becoming competitively probable to absorb the pump frequency of light here rather than here. So it's taking away from both the absorption efficiency and it's taken away from the emission stimulated emission probability. Are you with me? Jolly good. So, we go away from České Budovice back to Řež, thinking, okay, finally now we understand, at least now we understand what's going on. Okay, what we need is we need to keep the quantum yield of emission high, of course. We need to increase the ground state absorption, so increase the efficiency in which the pump is being absorbed. And then we need to decrease the excited state absorption. And to help that, what we need to do is to shorten the lifetime. Because, of course, the shorter the lifetime the species are here, the smaller the chance there is of them absorbing the emission energy and going into excited state absorption. Are you with me? So this now is what the criteria were. This is where what comes important now is actually some work which the gentleman here worked at the back, and this is something which was driven as well in terms of a lot of the lab work was done by this gentleman. This is Marcel N. And this work here was chlorination. You remember one of the things I mentioned on that slide, we're making these chlorinated molecules. Okay. Wojciech here, he did some calculations on these chlorination molecules. And what we found in these chlorination molecules, when I returned from České Budějovice, gave me an idea. Because what we published, what we found out about some of these chlorination molecules is that if, for example, you chlorinate at certain positions, you lose the quantum yield. The quantum yield of luminescence goes down, which is bad. But the lifetime in the excited state goes down as well, a lot. And so we began to think, well, can we use this? Because what we do, our hypothesis now is that we're losing laser emission because of excited state absorption. And excited state absorption is dependent on the lifetime of that excited state. And we're too long at the moment. Can we use chlorination or combine chlorination to reduce the lifetime of the excited state and combine that with the lift in fluorescence quantum yield from the alkylation? So, back in the lab, what we did was we made this species here, where we combine, on the B18 molecules, we've got 2 atoms of chlorine and 12 methyl groups. What we find is that, indeed, we achieve a drop in the lifetime of the excited state from 11.2 to 8.4 nanoseconds. We drop somewhat the quantum yield of emission. However, we gain considerably. This is B18, and this is the new species here, the 12-methylated dichlorinated B18 molecule. We gain considerably more in the absorption frequency. So we're going up in ground state absorption. We're going down in the lifetime of the excited state. So we're thinking this molecule can help us find out whether our hypothesis is correct. So what we did was got the next plane to Madrid. And, before we did that actually, before we got the plane to Madrid, we got the train down to, I drove, down to České Budějovice, and we measured on the excited state absorption. And what do we find? We find that our new molecule indeed has this negative absorption, this strong emission, okay, and we don't have the problem of excited state absorption so much. We go to Madrid and bang, it lasers. So that's a story about how we're developing our work and our research and how we're using these iterative procedures of going deeper and deeper and deeper, understanding more, producing hypotheses, and eventually coming to solutions into how these molecules can really work well. And I want to finish, however, on letting you into a bit of a secret. Because although we're continuing with this work, we also are expanding into a new dimension of boron hydride chemistry and physics. And this is a new project. We've successfully gained European funding. This is in the Horizons Pathfinder project. And the project's called Vortex for Fusion. And we are one of 7 members of a consortium of scientists from Finland, Germany, Britain, and the Czech Republic. And we are now looking to use our knowledge, our part is our expertise in the boranes, to see whether they will work as a boron-proton fusion fuel. This means that up until now, our expertise has been on the electronic excitation. Now I hope you feel like semi-experts at understanding the electronic excitations in B18H22. Well, what happens if you pump not with microjoules, which is strong? What happens if you pump with megajoules? Then eventually these electrons will be released from their molecular orbitals, and the whole system, the whole compound, will form a boron-proton plasma. And the question then is can we combine with physicists who are developing new structures of light, these special orbital angular momentum structures of light, which are interacting with our clusters in particularly strongly. And then can we use this advancement in laser technology to see if we can generate boron-proton plasma, which then, if we pump hard enough and we can achieve confinement, inertial confinement, where we shoot with lasers from all different angles, can we precipitate and form this fusion reaction, which would convert boron and proton nuclei ultimately into 3 alpha particles and thus generate electricity. We're at the beginning of this. The preliminary work is indeed very exciting. Here's some of the diagnostic outputs where we're starting the work with working with the PALS. You may have visited that in Ladvi at the Institute of Plasma Physics, where we can use a Gaussian laser, so we're not onto the angular momentum light yet. That's under construction in Finland. But we can use a Gaussian laser where we're hitting our targets, and the preliminary results are indeed that we're forming these large spots here are pretty conclusive evidence of the formation of helium nuclei. So it looks to be promising. And so I'd like to finish that if any of you here would like to join this particular adventure, then there's money and space in my laboratory. So if you are interested, you can look at our website. This is the website of our institute. This is the website of this European project. And this is my own personal website. If you are interested, if you're looking to do a PhD in a very high-risk, high-gain new area of chemistry where chemistry and physics combine, then please do look us up and send us an email or telephone me up or whatever. And with that comes to my conclusion. So I'd like to thank you in particular for allowing me to come. Here's a list of some key members of the group who have contributed. Many other boron brothers and sisters, including the 2 at the back there. Gentlemen, your names did not fit in, I'm afraid, but next time I'll try and fit you in the mists of this. Of course, is Rzeź. So if you do decide to join the team, this would be your average morning walk to work across the Vltava during the periods of early winter and early spring. I suppose a thank you to Gacha for financing a lot of the early work I was talking about, and a big thank you to EU Horizons for opening up this new exciting prospect of which you might join in helping me resolve. Thank you very much.
So let's open the discussion.
Yes. Yes, sir.
I have a question. You finally created a laser dye at the end. Is there anybody using this dye in lasers?
Not yet. Not yet. But hopefully, maybe one day soon. Yeah. So that final result is something which is new, very new actually, and indeed is something which we're still working out how to proceed with the result. So, but yeah. So at present, no use of it yet. But who knows? Maybe one day soon.
And I have another structural question.
Yes.
For me, chemistry always was about equilibrium.
Yes.
And I can imagine also that these two isoforms of B18,
yes,
that there is some equilibrium in between these two isoforms, that the syn and anti form switches in between another. Is it described that this actually happens, or it just takes 1 billion of years to actually happen?
So the only conversion of one isotope to the next, the only example in the literature, is a paper of mine, and that was only achieved when we inserted an extra atom of boron into syn B18H22 to form a B19H21 minus. And then, when I added formaldehyde and water to remove one vertex, the one that removed, there's a 50-50 chance that it goes to anti or syn. So I could go from pure syn to B19 and then degrade B19 back to B18 to a 50-50 split. So it's sort of around the houses route to get from syn to 50% anti. That's the only example. So otherwise we can't. We've tried lots of. It's a fascinating question, because if we did have something that could do that, that would be a huge help. And I've spent a lot of lab time trying to make it happen, but that was the only way I achieved it. We've tried, for example, hitting it with prolonged exposure to UV light. Would it isomerize? But we don't get any isomerization. And so it seems to be that the linkage, where it's linked like that for the anti, okay, sharing this edge, or like that for the syn, once it's locked there, it's locked there. So only if I add another boron atom, then it can here. If it removes the one here, then it gets to that conformation. That's the only way. So good question. Would love to find a way to do it, but so far nobody's managed it.
Mm-hmm.
So I have a follow-up question on this derivative. Have you tried measuring circularly polarized luminescence of the anti and syn, because this would open up some new possibilities? Maybe?
Yeah, excellent question as well, and also well done in spotting that indeed that the syn isomer is a chiral compound, and there is chirality there. The short answer is we've done very, very little work on that, and that's something which might become increasingly more important when we're now interested in the interaction of these compounds with orbital angular light, which has an orbital angular momentum. So that's something actually which we're going into now. So yeah, no results that I'm able to talk about as yet.
And another question: will you maybe dive into quantum dots in these compounds?
That's also something which we would. We've done some preliminary work about that. In that we've done. We were interested to see if we could get these nano aggregations of these molecules. If we, for example, have highly concentrated THF solutions that we drop into water and they begin to sort of aggregate around there to form something which then could lead up to something which we then could encapsulate with other species to form like a quantum dot. But yeah, we didn't take that any further. But again, fantastic idea. If you'd like to have a go, then you're welcome to start.
Actually, that was my question, if it's mandatory to have a PhD student for this, or if it can be a postdoc.
Well, I could speak to our director whether we could make it into a postdoc, yeah.
Yeah. You see, Virka is PhD student, so he cannot start
So
again.
are you, what's your PhD? What are you currently working on?
I'm working on polarized Raman and circular polarization measurement.
Yeah?
So that's quite a question.
Well, that could be. And when do you finish?
Within a year or so.
Really?
I will edit the question to what year I'm in. I'm in third year.
Sorry?
That I'm in third year of my studies.
Yes. So you're coming to a conclusion-ish.
Yeah.
Well, I mean, you know, these are certainly your expertise would be fantastic to. Maybe you know, when you feel in a comfortable position to do so, I'd like to maybe listen to. Were you planning to give a talk in your last year of a PhD? I could listen to or a bit about your work. I'll read some of your papers and see if we can form a collaboration, because that would be good, definitely.
Okay, let's remove the spot of the light on you. Sorry. More questions there? Mm-hmm.
Have you ever tried to synthesize and measure the properties of bigger structures?
So we've got one publication out, which is a theoretical paper about what happens if. So remember, I began with decaborane and then explained that if you nominally fuse two together, then you get the B18. And so the question is, well, what happens if you continue? And again, there's been many, and during my PhD, I spent a lot of lab time trying to do that, and nobody's achieved that. For some reason, it seems as if the reactivity of those boron edges diminishes once you've got two together. What I was successful in is I was able to get a boron atom inserted to get to the B19. And then I was using, part of my PhD was actually, the concept was to use metals, which are redox flexible, have all those extra orbitals and electrons about that can link two B18 clusters together. So I managed to do that, and we published, you know, if you link two together, so you've got B18 linked by a metal, palladium worked well, and then another one. But it can also work with platinum and mercury. And then we tried for a while with the mercury linked one to abstract the mercury with sulfur and to see if it would click. But as such, no success yet. The theoretical paper which we've got published, the reason why we published that is because, of course, we're thinking those lines. It's like, you know, with the organic systems where you extend the delocalization network. So that was the idea, and we were interested in, if they were difficult to make, we could at least calculate what would be the predicted photophysical properties, which look very good. But it's a massive synthetic challenge. What I can tell is we did put in for one Gacha proposal to support work for this very topic, to these extended fusions. But unfortunately, in Gacha, in their wisdom, decided not to give us the money. But you know, if you've got any ideas, or if you've got some experience in these, you know, we can go for it. There's the fusion of borane clusters is a fascinating subject. I could give a nice talk about just that. You know, what are I could go deep into the synthetic methods that do work for these things. You can generally they're either based on oxidative fusion, using iodine, for example, or they can be done with acids, or the other option is to use metals. But the problem with metals is they often deliver all sorts of different products and byproducts and metallations, etc. The acid or iodine oxidations tend to be cleaner, but as yet none of these methods have worked for clipping together B18s. We've got some recent publications that from this work we published how we've been successful in getting really good yields for anti-B18 specifically on fusing together smaller boron hydride molecules, B9 based boron molecules using these procedures. So that might be of interest to you to read those, but we can't get beyond B18 yet.
Well, I would have one naive question regarding the substitutions you tried. So maybe I didn't catch it from all the stories you showed us, but if I didn't, there's no aromatics used as a substituents, right?
Yeah, wow, you're good. That's correct.
So my question is, if you have tried, why they are not there? Because, the following up my naive thoughts is that if you consider that might be possible that the aromatic compound would absorb the light and emit it in the wavelength that it's absorbed by the borons, and that's like that it would be additive to the other absorbing light that you would elucidate the compound. So
I'm sure the two chaps here this will be a familiar conversation. So excellent question. And it's a question which we've spent, many hours and many bottles of wine trying to think about how we can achieve it. So, for example, let me give you, in these methylations, in these alkylations, okay? The alkylation is classic organic chemistry. It's aluminium trichloride catalyzed with the alkyl iodide, okay? It works really nicely for methyl iodide. It works really nicely for ethyl iodide. Propyl iodide, you get iodination, you don't get the propyl on. Butyl iodide, you get iodination, you don't get the... and of course, if you use aromatic, if you use phenyl iodide or something, then you don't get phenylation, you get iodination. Mm-hmm. So the classic, a lot of the classic organic techniques to get those aromatics on end up into some of these species here, which are interesting in their own rights, but they're not. We had exactly what you said was a fantastic question. And it's clear to me that this is an establishment that does great chemistry and a good chemistry brains, because all the questions so far have been fantastic. And yes, it has been a long-term goal to get an aromatic ring there. Specifically for those purposes to boost the absorption, and we're thinking that it'll boost the absorption. So we've tried more traditional routes. They fail. Then we've tried others, such as, for example, one of the main reasons why we went into alkylation, halogenation, is that we can then maybe take a species like this and do some sort of coupling reaction to stick the aromatic on there. That has not worked for us yet. And we've even also tried to use very high pressure syntheses. We've had a bit of success, actually, although I can't really talk about it too much because it's still unpublished. I can talk about what I did do is we, for example, took this compound. Okay, so this is interesting. Do you remember if you get electrophilic substitution here and a nucleophilic attack here, but if you take this compound and you take benzene and you put it into sort of a stainless steel reactor and you heat it up for a long time at high temperature, high pressure, then what you get, and we've published this last year, is you get a phenyl here, at this position here, the 5 position, and then you also get another phenyl, you get monophenylated decaborane, and you can get diphenylated decaborane when you get the 5 and 10 positions phenylated. And these species are very, very luminescent. And so your question is exactly on the right line. However, if we try the same, but I can't talk about what happens when we try the same thing with B18, unfortunately, yet. But yeah, so yeah.
And sorry, when you say that you try that, what does it mean to you? Like in your lab, or some collaborators are trying?
This is in our lab. This is specifically with a. I haven't got the slide with me. I should have brought this up. This is in discussion with a friend and colleague of mine called Honza Demel, and he was reading our papers. We talk about our work together, and he came up one day with an idea that he wanted to take. We had the same conversations as you and I are having, and he said to me, "Michael, why don't you just put together benzene and these compounds and just really whack it?" and I was like, Honza, it's not going to work. And he said, lend me some compounds. So he took the compounds, and he took this, and he filled it with benzene, and as he described, he had this big oven. He put the oven to 250 degrees or 300 degrees, and he whacked it in the oven, and we jokingly afterwards called the method demylation after Honza Demel. And in terms of, because I often use the metaphor that a synthetic chemist, it's like being a Michelin-starred, cook, chef, where you're trying to combine very delicately different ingredients together to form these new, combinations. And I suppose I was a classically trained synthetic chemist in the sense that we're all the time using solvents, right? So if you're making potatoes, we're boiling the potatoes, and we might have perfect conditions to get the right. Whereas he was just taking these spuds, these potatoes, and he was just whacking the oven, and he was just really but it worked, and to my great surprise, and because then he came back. I remember giving him the chemicals, thinking it's a waste of chemicals, and then he came back the next day and said, "I've got this, and it's really fluorescent underneath the light." And so at first we thought, well, has he, linked two of these clusters together to form B18? But it wasn't the case. It actually worked, and he got the. And now we've been trying to understand how it works, because what is the mechanism? Because I mean. If I take decaborane and I put it into benzene and I boil it and I reflux it, for a year, nothing happens. But if you stick it into an oven and close it under pressure, then it does react. And so we've published those results. What we haven't published are what we don't understand quite yet, and that is what the mechanism is.
And sorry, what is the yield?
It's good. For the mono, I'm trying to remember because we recover quite a lot of decaborane from it, which remains unreacted, and I think if you take that into account, it's something like 48% from memory. And then to a less degree, you've got dye substitution here and here, and the dye substituted molecule is even more luminescent. We also see evidence for tri-substitution as well, but we didn't get an X-ray structure for that. We just got mass spec and NMR.
Thank you.
Yeah, thank you.
So if there is no other... one more.
This might be a dumb question.
No question is dumb.
When substituting one of the hydrogens on the molecule, could you just put some chromophore function group, which absorbs in the 400 nanometers? Was that explored, or is that?
No, it's definitely that's sort of like an antenna. That's definitely been a long-term goal of us for a long time. We just haven't been. So the approach we were thinking about would be the halogenation, and then afterwards a coupling reaction with whatever, as you said, whatever the chromophore might be. But so far we've not succeeded there. But to tell you the truth, I mean, we've just scratched the surface on that, really. That's something which, for a long time, it would be great to go. It's question of number of hands, number of people working on it. Yeah, so that's all I can say really on it. I think it's not a stupid question, it's a good question, and it'll be lovely to find out what would happen. But so far we've not succeeded in making those.
No more questions?
Maybe I have one question. These molecules, they are actually quite like aesthetically pleasing.
Yeah, I think so too.
Do you know if there are any? But they are man-made, right?
Yes.
Are there any structures in nature that resemble these?
Well, I suppose the boron hydrides, they bridge this structural continuum from very condensed cluster type structures that we find in the late transition metals like gold and the rest of it. They structure from there as it transitions to the open chains and rings of carbon hydride chemistry, then that in between, that transitional phase could be the boron hydrides. But no, there's no these polyhedra. I mean, gallium also forms similar type of polyhedra, but they're usually capped with other things. So yeah, they're quite unique. I would say, you can argue the similarity of things like gallium, I suppose, but otherwise, these sort of discrete polyhedra. You see polyhedral. You see these. They're called deltahedral because they're based on triangular motifs. You see that sort of deltahedral pattern, as I said, in condensed metal structures. But of course, these are huge arrays rather than discrete molecules. So yeah, there's a good textbook that was written by, I thought, was it Mingos? And he was specializing, I think, on cluster chemistry in the P block and transition metals. And there's some interesting, he writes very nicely as well. And so I've got that book at home. So if you're really interested, I could always lend it to you. But yeah, so there are some similarities with other elements and how they condense, but really there's no equivalent of these sort of discrete polyhedral molecules.
No more questions? If not so, thank you very much for the great lecture again.
Well, thank you very much for the invitation and for your patience and kind attention. Thank you very much.
Thank you for the fruitful discussion. And so hopefully we will see each other the next year on some other event. So have a nice Christmas, have a nice New Year, and see you. Goodbye.